we're the team from St. Joseph's College, and this is the title of our paper. So what our research is about is we are considering functions that look like this, and then we consider the images of rational numbers under this function. Right. So for the presentation, we're first going to consider I'm first going to introduce what kind of FIFs that we are considering. By the way, FIF refers to fractal interpolation function. It's quite long, so I'm going to just say FIF. So and then after that, I'm going to talk about the three main results that we proved, and then I'm going to mention this error at the end. So first of all, the FIF's definition is quite general. So we have chosen these parameters to specialize to the case that we care about. So you can read our paper for what these parameters actually mean. Now, after we specialize, these are some equivalent formulations of the function that we are considering. First of all, one of the conditions is that it satisfies this functional equation. So if it is bounded and it satisfies this functional equation, then it is of the type that we are considering. And another one is closer to the one that Barnsley originally stated in his paper, and that is this one involving the affine functions. And a third condition is this visual one. So I'll just focus on this visual one first. It's the unique function that is the intersection of all of these rectangles. So the way you make the function is you take the unit square and then you contract it into these two rectangles repeatedly, and then the function will be going through all of these rectangles. Now, how this relates to the commutative diagrams is because it turns out that it maps so you can think of it as you can think of the function f as mapping the closed unit interval into these the horizontal sides of the rectangles, and then after f, it maps the vertical interval into these intervals. So that is how they relate. And next, and then so there's a standard argument that shows that this FIF exists because it is actually a fixed point of this contraction mapping, and so I'm not going to say much about this because it's very similar to the proof that there is a fixed point of an iterated function system. I'm just going to point out that this shows that there is a unique bounded function solution to the functional equation. So this is how you can get the function. And next, I'm going to talk about theorem 1. So once we see this function, we want to think about whether or not rationals get sent to rationals. And now it turns out that they do. So for example, f of 1/3 is 1/7, and f of 1/5 is 5/77, and so on. And then we can actually prove this. So to explain how the proof of that theorem works, I'm going to show you the computation of f of 5/12. Now, you can actually compute this by substituting 5/12 into this functional equation, where this is the functional equation condition that we said when we introduced the FIFs. So if you put it into the functional equation, then it turns out that you can substitute it and to reduce the problem to finding from this to finding this, and then to finding these two, which can be done simultaneously. And this actually relates to the binary expansion because 2/3 is 0.1010 and so on in binary. So this is the binary expansion. And then once you have these, you can actually go backwards and calculate that. Now, that is basically how we prove theorem 1. So here you notice that there is this non-periodic bit, and then this is the periodic bit. So we can consider the periodic case in this presentation for simplicity. And in that case, if we assume that P over Q has an odd denominator, then it has to have a periodic binary expansion. And then that means it's going to be a fixed point of this top row. Now, why that is because these L0 and these L1, they can be thought of as having as adding a 0 or a 1 respectively onto this initial bit of the binary expansion. So after you keep adding zeros and ones, where you have a1 and equal to 0 or 1, then it's going to be a fixed point because it's periodic. So then, therefore, P over Q is a fixed point of this top row, and so F of P over Q is going to be a fixed point of this one. And because these are affine functions with rational coefficients, it's going to be rational, and that's basically how you do it for odd denominators. And then after that, you can extend it to even denominators pretty similarly. So we would expect that if x1 is not 1/2, then you can keep doing this for the extended cases. But that actually is it can't be done. So I'm going to outline how you can prove that this doesn't work. So first, we want to consider. So we are considering the case when this is not 1/2. So let's consider the image of 1/2 under this function. Now that it turns out that by theorem 3, these two are both inverses and they are FIFs. So therefore, you can consider this, which is equivalent, this situation. And then theorem 2 says that because rational numbers always get mapped to rational numbers with odd denominators, it can't actually be 1/2, and therefore 1/2 doesn't get mapped to a rational number in this function. So so this is the statement of theorem 3, and then below that is the statement of corollary 2. And now we can actually view theorem 3 like this. So these are the various FIFs, and this is, and so if this is f subscript x1 y1, then its inverse is going to be f subscript y1 x1. And so it turns out that the inverse of this FIF is going to be an FIF, and that's how we can view it visually. So to prove corollary 2, which says that rational numbers get mapped to rational numbers with odd denominators, we just it's just algebra, so I'm not going to talk about it much. We just consider the denominators of the images, and then if we assume that D is odd, then this holds. Yeah, and then from that corollary 2 follows, and then we can get corollary 3. And then finally, theorem 4 is about how it relates to dynamical systems. So at the start, I mentioned that this function f, so this function f maps these contractions into another contraction. So more rigorously, it maps this dynamical system into this one. So this right one is the dyadic transformation, which deletes the first digit of the binary expansion, and then this one is a kind of similar looking one. And then so theorem 4 can be seen as kind of like a contrapositive of theorem 1. So in theorem 1, we use that, for example, P over Q has a periodic binary expansion to show that it gets mapped to a rational. But then because of theorem 3 and corollary 3 and so on, F doesn't necessarily map rationals to rationals. And so we can actually use this to show that rationals are not eventually periodic under the transformation T, which superficially looks similar. Yeah. And lastly, I'd actually like to mention a slight error, which turns out to have an interesting consequence. So at the start, I mentioned that, there is a certain functional equation that characterizes FIFs, right? So that equation can be seen here, but instead of the domain of F, we can put the closed unit interval. So this is an equivalent characterization for the FIF. So I said that there is one unique bounded solution, but it turns out that if there is an if we don't assume boundedness, then we can actually construct uncountably many discontinuous solutions. And we only realize this after the paper was submitted. So to construct these discontinuous solutions, you can consider this equivalence relation. Oh, yeah. And thank you for listening.